Talk to anyone about prehistoric oceans, and they'll tell you the same thing. The deep sea was the worst. The abyss. The crushing dark of the open Pacific, the Tethys, the great prehistoric basins where leviathans the size of buses cruised through black water looking for things to kill. That's where the monsters were. That's the rule, right? Deeper means scarier. Open ocean means apex predators. The further from land you are, the more dangerous it gets. Here's the thing. That rule is wrong. 85 million years ago, the single most dangerous body of water on planet Earth wasn't an ocean at all. It wasn't deep. It wasn't dark. It wasn't even particularly large by oceanic standards. It was a shallow sea, warm, sunlit, in most places under 200 meters deep, shallower than the average lake bed. You could have stood on the bottom of large sections of it and your head would have stuck out of the water, and it cut North America completely in half. From the Gulf of Mexico all the way to the Arctic Ocean. A 3,000-kilometer-long, 1,000-kilometer-wide inland sea sitting on top of what is now Texas, Oklahoma, Kansas, Nebraska, the Dakotas, Montana, Saskatchewan, all the way up to the Northwest Territories. The Western Interior Seaway. And it was full, packed, saturated, overstocked, with the most efficient killing machines that have ever swum on this planet. Not in the deep ocean, not at the edges of the world, in the middle of a continent, in water you could wade into. This is the story of the warmest, shallowest, sunniest, most beautiful sea in the history of North America, and why nothing in it should have ever existed. To understand how this sea existed at all, you have to forget the map of North America you grew up with. 85 million years ago, the continent looked nothing like it does today. The Rocky Mountains were just starting to rise. The Laramide orogeny was pushing them up from the west. The Appalachians on the east were older, lower, weathered. And between them was a low, flat, sagging trough. Geologists call it a foreland basin that had been slowly sinking for millions of years. At the same time, the planet was hot, catastrophically hot. The late Cretaceous was the warmest period of the entire Mesozoic. Polar ice caps did not exist. There was no ice anywhere on Earth, not a single glacier, not a single permanent snowfield, not even at the poles. When you melt all the ice on a planet, really all of it, the oceans rise. A lot. Global sea levels in the late Cretaceous were roughly 250 to 350 meters higher than they are today. Now combine those two facts, a low, sagging continental basin in the middle of North America, and oceans 300 meters higher than modern levels. The math is simple. The ocean came in. From the south, the warm waters of the Tethys flooded up through what is now the Gulf of Mexico. From the north, the cold waters of the Arctic Ocean pushed down through what is now the Canadian Shield. The two currents met somewhere over modern-day Wyoming and merged. The result was a long, narrow, warm, shallow inland sea, a continent-cutting strap of water that connected the Arctic to the tropics in a single, uninterrupted basin. At its widest, it was over 1,000 kilometers across. At its deepest, around 800 meters. But most of it, the vast majority, was shallow, under 200 meters, sunlit to the bottom, warm year-round, tropical at the southern end, temperate in the middle, cold but ice-free at the Arctic margin. It was the most beautiful sea you can imagine. Crystal blue water, white carbonate sand beaches, vast shallow shelves where light penetrated all the way to the sea floor, coral reefs along the warmer edges, lush coastal forests rising up from the shorelines, pterosaurs cruising overhead, sea turtles the size of cars, ammonites the size of tractor tires drifting through the water column. It looked like paradise. It was anything but. Because everything about this sea, the shallow depths, the abundant sunlight, the warm tropical water, the enormous productivity, created the perfect conditions for the most concentrated predator population that has ever existed in any body of water in the history of Earth. Let's get in. Imagine you're standing on a beach in what is now central Kansas. The sand under your feet is white, almost blinding in the sunlight. The temperature is around 30 degrees Celsius. The air is humid, salty. You can hear waves, gentle ones, lapping at a long, flat shoreline. Pterosaurs cry overhead, circling like seagulls but with 5-meter wingspans. The water in front of you is a brilliant turquoise, clear. You can see the bottom. It's maybe 2 meters deep where the surf breaks. Sand and small bits of broken shell. You wade in, knee-deep, warm. The water is body temperature. You can see your feet perfectly. Small fish dart away from your legs, little silver flashes no bigger than your hand. Chest deep, maybe 50 meters from shore, still completely clear. You're standing on a shallow shelf that extends for hundreds of kilometers in every direction. Around you, the water is full of life. Ammonites, coiled shell relatives of squid, drift past at eye level. They look like nautilus, but bigger. Some are the size of a dinner plate. Some are the size of a manhole cover. Ahead of you, something breaks the surface. A long, thin neck, 3 meters of it, followed by a small, fanged head. The head dips down. The neck disappears. Then comes the body, fat, barrel-shaped, 4 meters long, propelled by 4 enormous flippers. It glides past you 10 meters out, hunting fish. That's an elasmosaurus. It ignores you. You're too big, or not the right shape. Or you don't smell like food. Whatever the reason, it's not interested. It passes within touching distance and keeps moving. You start to relax. Don't. Above you, a shadow crosses the water. A pteranodon, wingspan of 7 meters, head crested like a hatchet, circles low, looking for fish near the surface. It dives, wings folded back, and stabs the water 30 meters from you. Comes up with a half-meter fish wriggling in its beak, climbs back into the sky, swallows the fish whole. That happens roughly every 2 minutes somewhere within your field of view. Pteranodons hunting in this sea numbered in the millions. The fossil beds of Kansas, the Niobrara chalk, preserve their skeletons in such quantity that they outnumber every other pteranodon-bearing site in the world combined. You take another step forward. The bottom drops away. You're now in maybe 10 meters of water, still clear, still warm. You can see all the way down. The seafloor here is covered in inoceramid clams, flat, scallop-like bivalves the size of car tires. Yes, tires. Some species, like Platyceramus, reached 3 meters in diameter, bigger than a kiddie pool. These clams are filter feeders. They sit on the bottom in vast colonies, pumping seawater through their gills, extracting plankton. The plankton in this sea is so abundant, so unbelievably rich, that the sea floor is literally paved with giant filter feeders the size of furniture. That plankton abundance is the key to everything. That's what makes this sea the most dangerous body of water in history. Because where there's that much food at the base of the food chain, there's something at the top of the food chain that has gotten very, very big. You feel a current behind you. You turn around, and you see what's actually living in this water. The first thing you notice is the size. It's a fish, recognizably a fish. Streamlined body, forked tail, pectoral fins. But the proportions are wrong. The body is too long, the head is too big. And the jaw is gaping open at you, full of teeth that look like inverted icicles. 6 meters, 20 feet. Longer than a great white shark, and approaching you at maybe 40 kilometers per hour. Xiphactinus audax, the largest predatory bony fish that has ever lived, larger than any modern marlin, larger than any tuna, larger than any swordfish. 3 times the size of the biggest bony fish alive today. Xiphactinus was a pure ambush hunter, massive jaw, hinged for maximum gape. It could swallow prey up to 2 meters long whole. We know this because we have found it. Multiple Zoophactinus fossils have been excavated from the Niobrara chalk with complete other fish inside their stomachs. The most famous specimen, known as the fish within a fish, is on display at the Sternberg Museum in Kansas. It's a 4-meter Zoophactinus with a 2-meter Gillicus arcuatus, itself a respectable predator, preserved entirely inside its ribcage. The smaller fish swallowed whole, head first. Still articulated, probably struggling at the moment the Zoophactinus died. The leading theory is that Gillicus was still alive when swallowed. It thrashed inside the stomach. It punctured something vital. The Zoophactinus suffocated or hemorrhaged with its meal trapped inside. Both fish sank to the bottom together. The chalk preserved them in that exact moment for 85 million years. That's the kind of hunter we're talking about. An animal so aggressive it would eat prey that could kill it from the inside. And there were thousands of them in this sea, tens of thousands, possibly hundreds of thousands at peak population. Zoophactinus fossils are so abundant in the Western Interior Seaway deposits that paleontologists sometimes describe finding them as almost trivial. 6-meter predatory fish. Almost trivial. If a Zoophactinus came at you in chest-deep water, there is no scenario where you survive. It doesn't even need to bite you. The impact alone, at 40 kilometers per hour, from a fish weighing 400 kilograms, would break your ribs, your spine, your skull. Whatever was left would be eaten in 2 pieces. And the Zoophactinus is not the apex predator. It's not even close. It's somewhere in the middle of the food chain. Above the Zoophactinus is something that eats Zoophactinus, the Ginsu shark. Cretoxyrhina mantelli, roughly 7 meters long, about the size of a modern great white, but with proportionally larger teeth, a more powerful bite, and an attack strategy that paleontologists describe, and this is a direct quote from published papers, as extreme ferocity. The Ginsu shark is named after the knife brand because that's what its teeth looked like, triangular, serrated, up to 7 centimeters long, designed not for grabbing, not for holding, but for slicing. A great white grabs and shakes, a Ginsu shark sliced. Imagine that for a second. A 7-meter shark that doesn't bite you to hold you, it bites you to cut you in half. We know how Cretoxyrhina hunted because the fossil record is unusually clear on this point. We have multiple specimens of mosasaurs, plesiosaurs, sea turtles, and Zoophactinus with Ginsu shark tooth marks on their bones. Bite radius, trajectory, force, all preserved in the fossilized scars. The pattern is consistent. Cretoxyrhina attacked from below, vertical strike, targeted the soft underside of prey, the belly, the throat, the flippers. Single bite, massive damage. Then retreat to let the prey bleed out. This is the same hunting strategy as a modern great white. Except the Ginsu shark was bigger, faster, and had teeth designed for cutting rather than crushing. One particular fossil, a pteranodon wing, preserved in Niobrara chalk, has a Cretoxyrhina tooth embedded in the bone. A flying reptile, snatched from the water surface or just above it by a 7-meter shark erupting from below at full speed. The shark didn't even need to surface fully. The bite happened underwater. The wing was severed. The pterosaur, bleeding, broken, fell back into the water. The shark circled, came back, finished the job. We have the tooth, still in the wing. 85 million years later. There were enough Ginsu sharks in this sea that they showed up in essentially every depositional layer of the Niobrara chalk, continuously, for roughly 10 million years. The population didn't fluctuate. It didn't crash. They were there, every day, every season, for 10 million consecutive years, hunting everything that moved. And they were not the apex predator either. There was something else, something that ate sharks. Tylosaurus proriger, 15 meters, 49 feet, 3 tons of muscle, scale and tooth, the largest mosasaur of the Western Interior Seaway, and one of the largest marine predators that has ever lived in any ocean, anywhere, at any point in Earth's history. To understand a mosasaur, you have to forget the word lizard.
Yes, technically, mosasaurs were lizards, closely related to modern monitor lizards and snakes. But that's like calling a fighter jet a metal bird. The category is accurate and useless at the same time. Tylosaurus had a body shaped like a torpedo, long, streamlined, muscular, built for explosive acceleration. 4 limbs converted into hydrofoils, not paddles, not flippers, but true hydrofoils that generated lift and let the animal maneuver in 3 dimensions like a submarine. A double-hinged jaw. The upper jaw was not fused to the skull. It could flex independently. The lower jaw could split at the chin, allowing the mouth to expand laterally. Combined, this meant Tylosaurus could swallow prey nearly its own diameter. A second row of teeth on the roof of its mouth, pterygoid teeth, curved backward, designed to grip prey while the main jaw is repositioned for swallowing, and a battering ram for a snout. The end of the upper jaw, the rostrum, was a solid, reinforced, bony projection that extended beyond the teeth. Paleontologists believe Tylosaurus used it as a ramming weapon, the same way orcas use blunt force to stun prey. Tylosaurus killed by ramming first, biting second. Picture that. A 15-meter predator accelerating to attack speed, estimated at 50 kilometers per hour, and slamming a reinforced bony snout into the side of its prey. The impact alone could kill animals smaller than itself. The bite afterward was almost a formality. We know what Tylosaurus ate because we keep finding their stomach contents. Inside Tylosaurus fossils, paleontologists have recovered sharks, including Cretoxyrhina remains, other mosasaurs, plesiosaurs, sea turtles, pterosaurs, diving birds, large fish, smaller mosasaurs of its own species. Cannibalism. Tylosaurus ate other Tylosaurus, routinely. This is an animal so dominant in its ecosystem that the only predator capable of killing it was itself. There was no apex predator above Tylosaurus in the Western Interior Seaway. There was nothing in this sea that could threaten a fully grown adult Tylosaurus. It killed Ginsu sharks. It killed elasmosaurs. It killed Xiphactinus. It killed pterosaurs that flew too low. It killed sea turtles by crushing their shells. It killed its own juveniles. It killed other adult Tylosaurus during territorial disputes. And there were thousands of them, across 3,000 kilometers of sea, for roughly 12 million years. You are standing chest-deep in water with no apex predator. The food web has no ceiling. The largest, most aggressive, most efficient marine predator of the entire Mesozoic is somewhere within a few kilometers of you, right now, hunting. And the water is so clear, you'll see it coming. Now here's the part that should genuinely disturb you. Everything I just described, Xiphactinus, Cretoxyrhina, Tylosaurus, those animals existed in the open oceans too. The Tethys had mosasaurs. The Proto-Atlantic had sharks. The Pacific had predatory fish. So why was the Western Interior Seaway worse than the actual ocean? 3 reasons. And once you understand them, you'll never look at a shallow sea the same way again. Reason 1. Density. In the open ocean, predators are spread out across enormous volumes of water, most of it deep, dark, and empty. A Tylosaurus in the Tethys had hundreds of cubic kilometers to patrol. Encounters with prey were rare. Encounters with other predators were rarer. In the Western Interior Seaway, the entire sea was shallow, under 200 meters in most places, which meant the entire water column was productive, sunlit, oxygenated, full of plankton, full of fish, full of everything. Predators didn't need to dive deep. They didn't need to range wide. The food was concentrated in a thin, shallow layer covering 3 million square kilometers. Predator density was, by some estimates, 5 to 10 times higher than in the open oceans of the same era. Reason 2. Visibility cuts both ways. The water was crystal clear. That sounds nice, but in clear, shallow water, everything can see everything. There's nowhere to hide. There's no thermocline to disappear below. There's no kelp forest to vanish into. There's no abyssal darkness to retreat to. If you were prey in this sea, and at human size you absolutely were, every predator within several hundred meters could see you, all the time, constantly. Reason 3. Convergence. In the open ocean, the food web is layered vertically. Surface feeders, midwater hunters, deep predators. They mostly don't interact. They occupy different zones. In a 200-meter deep sea, all the layers collapse into one. The surface hunters and the bottom hunters and the midwater hunters are all in the same water. The pteranodon hunting from above, the Zophanctinus hunting at mid-depth, the Cretoxorhina hunting from below, the Tylosaurus hunting everywhere. You weren't dealing with one predator. You were dealing with the entire predator community simultaneously in every direction, in water clear enough that they could all see you from a kilometer away. In the open ocean, you might survive by going deep, by going dark, by going still. In the Western Interior Seaway, there was no deep, there was no dark, and you couldn't stay still. The current would push you. You'd shift, you'd shimmer, and something would notice. The deep ocean was scarier in theory. The Western Interior Seaway was scarier in practice. This was the highest predator concentration in any body of water in the geological record. We have not found evidence of any marine ecosystem, past or present, with comparable density of large carnivores per cubic kilometer. It was, quite literally, the deadliest water in the history of life.
And then it was gone. 70 million years ago, 15 million years before the asteroid, the Western Interior Seaway began to drain. The Rocky Mountains, still rising, tilted the continent westward. Global sea levels began to drop. The basin started to fill with sediment from the eroding highlands. Slowly, the sea retreated, south and north. The middle dried first. The connection between the Arctic waters and the Gulf of Mexico was severed. The sea became 2 separate inlets, then 4, then a series of disconnected lagoons, then mudflats, then river channels. By the time the asteroid hit, the Western Interior Seaway had been gone for 5 to 10 million years. The mosasaurs had retreated to the open oceans. The Ginsu sharks had vanished. The pteranodons of the Niobrara chalk had been extinct for millennia. The deadliest body of water in the history of Earth ended not in catastrophe. It ended in quiet, in slow geological erasure, in a continent rising up and shrugging the ocean off its back. What it left behind was bones. So many bones. The Niobrara chalk, the geological formation that records this sea in central Kansas, Nebraska, and the Dakotas, is one of the richest fossil deposits in the world. Hundreds of meters thick, hundreds of kilometers across, composed almost entirely of the microscopic shells of dead plankton, with bones of larger animals scattered throughout like raisins in cake. You can walk across Kansas today and step on chalk that was once living plankton in the Western Interior Seaway. You can dig in a road cut in western Nebraska and pull out the tooth of a Cretoxorhina that died 85 million years ago. You can drive across South Dakota and pass quarries where Zophanctinus skeletons are excavated by the dozen. There is a small town in western Kansas called Castle Rock, population approximately none. It sits in the middle of farmland, sun-baked and dry, surrounded by wheat fields. And in those wheat fields, when the rain washes the soil thin, you can find, lying on the surface, just sitting there, fossilized vertebrae of marine reptiles. People mow their lawns over the bones of mosasaurs. Children play in dirt full of shark teeth. The deadliest predators in the history of marine ecosystems are now mulch, subsoil, rock dust mixed into Kansas grain fields. The sea is gone. The predators are gone. The pterosaurs are gone.
The plankton blooms, the giant clams, the elasmosaurs, the Ginsu sharks, the 15-meter mosasaurs. All of it. All of them. Gone. Dust. Stone. What's left is wheat. And here's the part that I think about when I think about this sea. For 30 million years, the Western Interior Seaway was the most dangerous body of water on planet Earth, the single most concentrated predator zone in the marine fossil record. And it sat in the middle of what would become the safest, flattest, most boring part of the United States, Kansas. The deadliest sea in history became Kansas. Civilizations don't last forever. Empires fall, cities crumble. But on geological timescales, on the timescales of this planet, even ecosystems are temporary. Even the most successful, most dominant, most apex predator communities will, given enough time, be drained, eroded, scattered, and plowed under by farmers who don't know they're walking on a graveyard of monsters. The Western Interior Seaway should make you uncomfortable, not because of what lived in it, because of how completely it disappeared. Everything dies, everything erodes, everything becomes wheat, and the most dangerous water in the history of life is now somebody's backyard. Next time, we're going to talk about a body of water that did the opposite, a sea that didn't slowly fade away, a sea that vanished, suddenly, completely, and then came back as the biggest flood in Earth's history. The Mediterranean wasn't always there, and the day it returned was the most violent geological event ever recorded in the rock. Until next time, stay curious, stay terrified.